Well, hello everybody, John Grimsmo here. Yesterday was Canada Day, a national holiday. We all decided to work yesterday and take today off. So today being Friday, so everybody can have a long weekend. But of course, being the owner of the business, I'm here by myself on Friday. Got a bunch of stuff to play with, and I thought I would bring you guys along. I love having the shop to myself when I can. It just lets me really quiet and focus and do the critical tasks that only I can do. Or that I want to do. So today is a good example of that. So with the Kern, I can actually log into the control panel from my computer or from my phone, anywhere, and see the status of the machine. See if it's still running. I can view the actual screen and see if the code is running, see how much tool life is left. I logged in last night and saw that there was a broken tool, and I said, okay, tomorrow is the day I'm fixing that for good. I have tools in hand, I've already purchased them, new style of tool to eliminate that problem again. So that is not going to happen again because it's been kind of an issue. So let me show you. Okay, so in here we have RAS candles. I'm going to tilt this back so we can get some better light on it. So in here we've got our RAS candles. Right now what I'm trying to do is I'm trying to slot out the lock bar slot more than halfway down with a 1/16 inch end mill, which is supposed to be right here, but it's broken. That tool clearances out a lot of the roughing where the lock bar insert goes, and then it goes in and it slots. And if you see, if I can get it to focus, you can see it starts to get fuzzy on the edges here, and that tells me the tool is definitely wearing. And deep inside there I can see the fuzziness. Right on top of my fingernail there I can see the fuzziness. Yeah, that tool is toast. And then it broke and it gave up. Now, one thing I have to be very careful of is that there's no broken carbide in that cut, still in there. So I usually get in with my loop, or if I can pull the part off, put it on the microscope. But I need to make sure that if there is carbide in there, I have to get it out. Otherwise the next tool goes in and it's going to destroy itself. It just doesn't work. I looked briefly, I'm going to look again closer. I don't think there's anything in there, which is good, which means I should be able to just continue. On the current control panel, if I go over to tool table, this is tool 59? 59. So I go to my tool table, tool 59, it is locked because breakage detection caught it as broken. It has a limit, I put a limit of 300 minutes on it. It is at 231, so it's up there in tool life. Maybe that 300 is too ambitious. Maybe I need to make it 200 minutes. I'm fine with that. I don't care how often I replace tools as long as they never break. That's my ultimate goal here. So maybe I'll do that. However, it doesn't matter because I'm switching to a different tool. This right here is the tool that broke. This is a 1/16 inch 4-flute stub end mill. I often use Lakeshore Carbide, but lately I've been using DeBoer tool. This is a Canadian company. They're like 45 minutes away. One day I'm going to tour their factory because they look like a very, very, very awesome place that makes carbide end mills. And they're cheap, and they're in stock, and they're Canadian, and they come immediately because they're super close, and that's awesome. So anyway, it's the same as the Lakeshore tool. This is what we typically use to slot out the lock bar slot. You can see here how it light all the way through. On the RASC I'm actually cheating a little bit. I go with the bigger tool halfway down, and then with a smaller tool I go all the way through, so that from the outside, the visible side, you get this very small cutout, yet on the inside it's actually like bigger and fatter. It helps with tool life because then I don't have a small tool going all the way down and breaking and causing problems. And this has been a really good, like, midway compromise. So you get the visible from the outside, but the tool life on the inside. But I'm still not getting the tool life that I want. So this tool's great. They're cheap. They're like $8 or $10 or something. But you still never want to break tools. You want to establish a system that never breaks tools. And that's perfectly theoretical, right? I've been curious about trying these things, these newfangled technology called a high feed end mill. This is our Niagara tool high feed end mill. Let's see if I can zoom in there for you. Okay, this is a 2-flute high feed end mill. that it's just got a different cutter geometry. Whereas this has side flutes that go all the way down and very sharp pointy corners, and it's also end cutting, so you can plunge. You shouldn't, but you can. This guy, it's got two little like hump radiuses as the cutting flutes, and you don't cut very deep. You cut, I think, 4 thou deep or something like that, maybe even 2 thou. Depends on the tool and everything. So you do very, very micro, like literally the width of a human hair, deep depth of cut. Very fast. Zip down, zip, 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 as opposed to a deep, slow plunge slot operation. Both work. They both take, give or take, about the same cycle time. I'm cutting titanium, and I've never tried a high feed end mill in this application, and I'm just super pumped to do it. In my head, it makes perfect sense because there's almost no cutting load going 4 thou deep and zipping across, and then 4 thou deep again and zipping across. I think it's like 60 passes down. But the machine is super fast, and I have tons of RPM, and I can do all of it with that. So I'm really excited to try this out in the nerd way that I can get excited about these things. So all I gotta do is mount it up in a RegoFix holder and touch it off, and I've already got it programmed in Fusion, and I just run it. Yeah, I'm gonna use a bigger end mill, see the size difference here, to explain like cutting load. You know, when you're cutting just a few thou deep, the tool doesn't have much force on it to bend and break. But when you're cutting like this deep, then you have a lot of axial engagement, a lot of force trying to bend the tool, trying to break the tool. All those chips now that it's cutting, every time it scoops out, they have to get out, and they have to not get in the way. And as the tool gets more worn and more dull and has higher cutting load, a tiny tool like this, it's just gonna snap. It's just gonna load up, it's gonna gum up with the titanium, they're gonna get stuck in the flutes because they're dull, and they're not sharp enough to like evacuate and shear the chip nicely, and it's just gonna snap right off. So that's the theory behind the high feed end mill is exciting to me because cutting loads are negligible. Also, they say that instead of transmitting the cutting loads this way, based on the flute shape and all that, they transmit the cutting loads mostly axially up into the tool. And that sounds kind of awesome. It sounds like the tool is going to last forever, theoretically. You know, way better than the other way. So, let's give this a shot. Step 1, replace previous tool that's broken, because I still need this for other stuff. Step 1.5, do a spindle warm-up while I'm replacing the tool. Okay, now that I've replaced the tool, you might have noticed that I used my 3D printed magnet adapter. So every time I take out a tool, I put this where it was so that I never have to think about where the tool just came from. Because literally, this is intimidating. If you pull out a tool, even 5 seconds later, you're gonna figure out where it came from. So I always put this, oh, the tool goes right there, so that next time I come in, I know where to put it back. And also notice, it's supposed to go this way. It's modeled after an HSK taper, but I've found if I install it upside down, then when the tool changer robot comes in, and I've had it try to grab this before, if it's right side up, it will actually grab it and change it, which is bad. But if I put it upside down, it knows that there's nothing there. So the upside down is just better. Okay, now that I've replaced the tool, the actual length of it is going to be ever so slightly different. So the machine has to know to touch it off again on the Bloom laser. We got this laser beam right here, laser tool setter. So a laser beam goes between those 2 points. This rotates, touches off the tool, touches it off for length and for diameter. And I used to have to do this manually, so I would, you know, replace the tool, and then I'd come over here and I'd call, which one? I would call tool setting probe, stop that. I would call this manually every time. That's dumb. I don't do that anymore. I created a script that all I have to do is I have to go to the tool table. The machine can be running this whole time. I don't have to be involved. I have to edit the tool table, make sure edit is on. I have to get rid of that lock, so that's not locked anymore. And then here in the time 1 field, I type 999. And there's a script in the background that knows, it reads this every tool change, every call. It looks for a 999. If there is one there, it will do the automatic touch off. This can happen 4 hours into a cycle. It'll happen automatically. It is absolutely the best. And then as long as my current time is not over my 300, so if this was 301, it won't even call a tool. It'll be just like as if it were locked. Almost just like it. But it's not, so I can leave it alone. And I would change I'm gonna change it to 250 anyway. We're not gonna be slotting anymore with this tool. We're just gonna be roughing out the lock insert part and doing some other stuff. So the 250 should be amazing. So the next time this tool comes up to 250, I will inspect it and look at it and see how the wear is under the microscope and see if it if that 250 needs to be tweaked. Step 2, install Niagara Tool high-feed end mill. I have a really hard time filming B-roll without talking and explaining everything to you guys, so it's going to be a bit of both. With so many tools in the kern, I have to manage which tool goes where and all the details of every tool. So I actually have 3 separate tool libraries, which is annoying, but it's working best for me. I have a Google spreadsheet that I created that tells me my new Seco high-feed end mill is going to be tool 94. It's a long quarter radius end mill. I've got this block of end mills that's set out to that. I've got some notes here. It's going to be sticking out 1/2 inch and it's going to be in a PG-15 holder. And I have this for all of my tools. So this tells me what tool goes where in my own database that's not in Fusion and that's not in the machine. The other database is in Fusion 360 where I program all the tool paths, and so that needs to know what tool is where. And then also the tool table here in the kern that we showed you. Did I set it? No, what did we say, 94? So 94 is empty right now. I'm gonna have to fill this in. There. Step 3, add the tooling information to the kern tool table and tell it to touch off with a 999 call. Step 4, make sure there is actually no carbide in that broken tool, broken handle part section. Okay, pretty sure we're good. Pretty happy with that. Just a little pokey screwdriver, loop. It's funny, I used to love these things. I used to use it for absolutely everything. And then I got the Leica microscope, and with the actual microscope, I almost never use this. But I can't carry the Leica into the kern, so this still has use. And these are like $8 on Amazon or something. They are awesome. Okay, so here I have my Rask cam file, my tombstone. Whole bunch of sketches and all kinds of little details and stuff. There's a lot going on in here. So I know I've already created a tool path. Blades, handle backsides. This is the current version of what I'm doing with the tool 59, the one that broke. If I go to simulate, so notice here how I have a pre-drilled entry hole. This is super important. That way I can just plunge into the cut and not worry about it. Now I come back here, do a little bit of clearancing, and then I'm slotting. So it's not a lot of deep axial engagement, but it's enough to make the tool not happy over time. Especially once it gets to here. Actually, I bet you that's where it broke. Let me check. No, it got farther. It did get farther than that before it broke. It broke about here-ish. But yeah, that's, I don't know, for such a tiny tool, that's almost probably more than 1 times deep, close to 2 times deep axial engagement. It just doesn't like it long term. But as we saw, I had 230 minutes of cutting time. It's a lot of cutting time. So I'm not unhappy with it, I just need a better solution. You know, I bet you it was in the Norseman handle file that I tested the multiple step down. So I'm gonna, give me a minute, I'll open that up, I'll copy the details into the RASC here, and we'll get it going. See, now with the Norseman we don't have that halfway down with the smaller tool all the way down. I have this 1/16 inch tool all the way down, doing a pretty deep plunge, like 2 times diameter deep. And it doesn't, oh, I do it in 2 steps, really? Okay, apparently I'm doing it in 2 steps. So on the Norseman, I am doing it in 2 steps. I know on the Mori, I thought we were doing it in 1 for the longest time, but the tool would break at weird times. This is why we're doing the high feed end mill, because I've wanted something like this for a long time. I want a better solution for this. We've been dealing with that broken tool for years. Okay, so if I unhide the unsuppress, no. Unsuppress that one. Generate it. Let's see what it does. Look at that. That's a lot of steps. I think I decided to, on the Seiko website, they list the speeds and feeds for this tool, and they list like a range, like minimum, maximum. I think I chose near the maximum range because I'm like, send it, just go, it'll be fine, maybe. Okay, so you can see down here in the corner, we got a 6 minute 32 seconds estimated cycle time, whereas the double slotting takes 7 minutes. So theoretically, this way is faster. If we look inside, we have speeds and feeds of 445 surface feet per minute, which is a buttload. That's a lot of RPM, 27,000 RPM. The current has a 42,000 RPM spindle, so this is no problem, but the Mori only has a 12,000 RPM spindle. This is asking for more than double of that. That's crazy. But yeah, 27,000, no problem. With a cutting feed per tooth of 1 thou, 3.5 tenths, so 13 tenths, which is booking it for a small tool like that. But our step down is only 3 thou, boop, 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 like literally the diameter of a human hair, deep, every time. And with, remember the bottom of that Niagara Seiko tool, it's like scoopy. And so that scoop, the scoop will not be buried, only a portion of the scoop. So as it's cutting the material, it's just like slivering it, like a potato peeler kind of thing. It's just zip, zip, zip. Very gentle cuts, very smooth cutting action. It should be quite amazing. It doesn't have those sharp pointy tips at the bottom of the end mill to break off and to degrade over time, to load up and see too much load in the corners. It's just scooping axially. So I'm excited for this. Okay, so what I'm gonna do is I'm gonna copy this entire tool path, which will copy the tool itself into the RASC folder. So all the speeds and feeds, all the data, all the everything, the tool will now go into the RASC tool library, and even all the step downs and everything. All I have to do is choose the new tool path, the line that it's following to do this. Okay, that'll take a minute. Okay, I gotta figure out what the depth of this contour is. I'm going to that face, which is there. See all the sketches, all the blue lines? I gotta get rid of that because it's distracting. There we go. Okay, so that step face is where I'm going to, on the old toolpath. The new toolpath, my depth is going to be to a selection. Where'd my model go? There we go, and my sketches came back, okay? So I'm going to that face. I want, yes, from the model top. I do I want to offset off the bottom? I'm going to offset off the bottom 1 thou. So because we're in a 5-axis machine and the machine is tilted, I need to tell this toolpath that Z is this way and X is this way, otherwise it's going to do it wrong. So for my Z axis, it's always up and down in real life, even though the table is tilted. So I just click any vertical line, and now you can see my blue Z line is pointing up at the sky. That's good. But I want my red X line to be pointing to the right. So I need to click a left to right line, wrong direction. I need to flip the direction. Now we're good. And that's all it is for tool orientation. For any 5-axis, 4-axis machine, it's pretty simple. You just make sure it does the way you want it to do, and then it will lay the toolpath in that orientation. Simple. Okay, now I need to choose the line that I'm going to follow. I actually drew a line because I'm picky and I want the tool to go exactly here and do exactly this. So I clicked it. Let me show you. I click it, not that one. Click it once, it only selects the one line. I click it again, and it's going to say, do you want an open contour or a closed contour? We want an open contour. So now you can see as I drag along the line, it says, do you want to go this far, this far? And if I go all the way to the end, it will now select that entire chain of lines. And then I hit the plus to accept it. That is now my toolpath. Just quick check, make sure everything's still good. Compensation is off because I don't want the tool to the left or to the right. I want it to follow that line on the center. Multiple step down, so 3 thou step, 3 thou finishing step, finish only at final depth instead of every step, no lead in, no lead out. I want to plunge, basically right at the beginning of that in the entry hole. This should do it. It's not going as deep, like we talked about, as the Norseman handle. So, and the Norseman is a longer lock bar as well, so maybe that all adds up to be a lot more cycle time. Something still feels weird about this. But I don't know. Also, you see this yellow retract line? That's where the tool is going to go every time. You got to make sure it's not going to run into a fixture or a clamp or a bolt or a feature or anything. Yeah, I mean, it's feeding at 75 inches per minute, which is really fast. Normally I would post the entire folder, all of the operations for this test, for the video, for you and for me. Even if I wasn't filming, I'm just going to post this one operation. I want to watch it. I want to, turn the coolant off and look and see and figure out what's going on. So let's do that. Let's post just the one operation. Post. Bring it into complete, open the proj file. Do some magic clicking. Alright, let's see what complete has to say about this. Complete is sweet. It models the entire kern. It kinematically moves it in every direction that it's going to move for this toolpath. It will tell you if it's going to crash or break a tool or do something it's not supposed to do. Okay, tool change. See, it tilts the B down, and that's all it's doing. Zip, 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 zip. Progress bar at the bottom here. Sweet. And then, as it's doing a tool breakage check, it complains because I haven't fixed that properly yet. It thinks it's crashing, but it's not. Pretty happy with that. It thinks it's crashing so hard. But everything is normal. Other than those things it's crashing at the end, everything's good. Okay, so I can post that, post, I'm going to post it into my kern folder, my rask folder, my handle backsides folder, and I'm going to rename it as high feed test. Try to be good about doing no spaces just because, and then I use this program called TNC Remo to transfer the file directly to the kern. Subroutines, handle backsides, should go there. And then I gotta find it on my computer. Rask, handle backsides, high feed test. Drag, drop, done. It's on the kern, let's go. So I've always said for years that CNC machining is not a spectator sport. You know, if you're watching this, you've probably seen other machining videos. You've probably seen all the super cool, sexy, beautifully filmed, slow motion, chips flying off. And that's amazing. It's hard to film that, especially with the coolant flying and everything. But it takes like dedicated effort to set up and tripods and film that, and it's great. But the actual totality of machining is what we just looked at, sitting in front of the computer for hours, days, weeks at a time, fine-tuning all these tool paths and thinking and analyzing and picking tools and purchasing and understanding what the tool is doing, how it's entering the material. You know, do you make an entry hole so that the tool can go inside so it's not overloaded? It's all this stuff it's not sexy to watch, but I love it. It's like Zen for me. It's challenging, it's difficult, it's confusing, drives me crazy, but I love it so much. And it's hard to bring you along on a journey that's like so slow and plodding all of the time. So I struggle with that, but I still think it's super cool. Before we get started, I want to explain just a thought that I had in my head about chip evacuation. So with the old tool, imagine if this flag wrench was my old end mill, it's about the same size. If it's deep in the cut and it's cutting sideways, the chips are now kind of long and they have to get out of the cut so that they don't get in the way of the next cut. The angle of the end mill helps with that. The flood coolant blasting it helps with that. Other things do help, but it's still kind of a long chip. Whereas now with this high feed end mill, only cutting down 0.03 of an inch, nothing almost, and they're scoopy chips. They're like potato chips. They are tiny, they're light, they're small, they're thin, and the coolant will just blow them away. They're not like deep in a cavity, struggling to get away from the tool and get out. So the more I think about these high feed end mills, the more they absolutely make sense for so many things, for roughing anyway. I'm excited. We're gonna go to the program button. I put these stickies on here to help me and the rest of the team remember everything. There's an edit one up here too. So we're gonna run, we're gonna open program management, we're gonna open where we put that file. We put it under Grimsmo, under Rask subroutines, handle backsides. I tried to make this all very logical for me and for the rest of the team, and it's working. It's working really well, separating everything. So there we got our high feed test. The touchscreen is fantastic. So it's a pretty short program, 500 lines of code, no big deal. Let's run it. I'm mildly nervous, but like nothing catastrophic is going to happen. Worst case is I'm just going to break the tool. But I don't want to do that because these things are like $70 each. And I only have 2 of them. But it should be goodish. Let's go. Okay, here I can show you my tool touch off. So, culling tool 94. I left the door open, the tool change door. Culling tool 94. Here we go. Now it's gonna go home, rotate, rotate. It's gonna touch it off. Slowly touch it off in length. Now it's going to touch it off in diameter. Diameter's not critical for this tool, but it has to do something. Okay. Now it's going to do a little dance where it switches to another tool, because in the tool table, I can't overwrite that 999 while the tool is in the spindle. So I have to to call another tool. Now I can overwrite the 999, and now I'm going to call that tool back. Okay, now I'm going to walk up and do this slowly. I'm going to turn the coolant off. Don't always recommend machining titanium without coolant, but I need to see what's going on. Okay, so because this tool is only going super shallow depths of cut, I'm not worried about the first few cuts being dry, and I'll be able to see the chips coming off of them. Should be good. So, interestingly enough, it's really cool. I'm able to pause the machine and turn the spindle off and open the door while it's still thinking in the cycle. So I can now look and see what's going on here. So I did 2 passes down, which is only 6 thou. The first one made quite a lot of chips. I was kind of surprised. Let's get up in here. So with the coolant off, which again is not ideal, but I want to see and I want you to see. Made a lot of chips. But look at the size of these chips. They're tiny. Tiny and consistent. They're like a light sand. Interesting. Oh yeah, see, I clear them away. That is a very shallow depth of cut. That's 6 thou. I can just see it. Sorry. I was looking, not the camera. Yeah, right in there. That's 6 thou. Looks like it. Man, this is great. I like this. I like this a lot. I'm really liking this. This is going to be fantastic. Cut quality looks fantastic. Okay. Let's get the coolant back going again, get rid of all this chips, dust, stuff. I looked under the microscope at the chips that are on my finger, and this is just so cool. I have to share with you guys too. So I've got my phone mounted on the little phone adapter right up there. Look at that little curly right in the middle. These are beautiful. I'm gonna dry them off on a paper towel so I get most of the coolant off. Let's try this again. Look at these little guys. Love it. For scale. Look at that. You can see even like how they're sheared. Awesome. That is super cool. Super duper cool. Dude, this is dust. This is titanium dust. As long as the flood coolant is working, it will blast this stuff away. I have zero fears now of loading up that tool with chips, like recutting chips. Okay, let's continue that. Full speed, full send. Let's go. All right, that's full speed. 74 inches per minute. That's doing a tool breakage check. Just real quick through the laser, see if it's broken. It is not broken. Success! Open the door, blow it down. Oh baby, that looks good. Okay, last note on this high feed end mill conversation is Since I still have my phone mounted on this plastic case that guy made for me, sent to me, it's amazing. Since I still have that, I want to get the Seiko tool under the... I keep saying Seiko. Seiko bought Niagara Cutter. It's made by Niagara Cutter, but it says like a Seiko tool company, so it's Seiko Niagara, whatever. Speaking of which, that's the tool for anybody curious. But yeah, I want to get this under the microscope so I can show you guys the difference. And then here I also have a De Boer high-feed end mill. We'll look at the flute geometry of that one as well. Alright, look at that guy. So there you can see the radiuses. I'm going to clean it off in my Rodico putty. So since your depth of cut is only super duper shallow, if I use my finger as a cutter, like there's touching the surface and your depth of cut is definitely not burying the flutes. I think the whole radius is like 8 or 10 thou deep. So you're not burying it, you're not even hitting this corner over here. You're just skimming it. So yeah, if I use the dirt on my finger as the chips, here's what we're doing. That's so funny. I got dirty fingers. Cool, eh? Okay, let's look at the De Boer one. This is a bigger one. This is 1/8 inch end mill. And it has a different geometry. It's fascinating. Much less pronounced scoopies. Got a radiused edge. Looks like it could even cut on the sides, cut a bit deeper if it wanted to. The Seiko had kind of a hole in the center, like a dip. Whereas this is a gentle radius all the way across. But it's going to do kind of the same thing. This might be a stronger design, I don't know. I'm not a tool maker. But it's kind of sweet to see how they were doing it differently. But you look at how strong this tool is. It's got a solid shape, not flutes going all the way out. It's amazing. I love it. So these end mills, they're not finishing tools, they are roughing tools. They are remove all of the crap you don't want so that your finishing tools can come in and do the fine detail work. I like them. I've known about them for, I don't know, 5-6 years. I've got one of my tooling reps keeps emailing me every couple months, like, oh, have you tried high-feed end mills yet? And I'm like, no, I haven't yet. But he was suggesting for the wrong application that interested me. And this lock bar slot is the right application that interests me. And it opens my eyes up to using them for many different other things. You know, they often sell them for hardened steels. And I cut a little bit of hardened steels, but not all. And I'm going to start using these for all kinds of stuff. So, win. Super success. I highly recommend them. They're more expensive than a traditional end mill, but they're not going to break. So, I don't know. Think about it. Just educate you guys a little bit. And rant on high-feed end mills. Alright guys, thanks for watching me nerd out about CNC machining and manufacturing and high-feed end mills and all that cool stuff. Microscopes. I enjoy sharing this stuff. I don't take the time to do it enough. I wish I could do more, but it's fun. So that is one of my 5 projects that I wanted to accomplish, that I will accomplish while I'm here in the shop by myself. I might not film the other 4, but we're busy. We're busy. We're super duper busy. Productive. Things are good. Shop is rocking. We got a staff of 11 people right now, and we need more. And everything's going awesome. So, hope you guys are good. Hope you're well. Enjoy Canada Day, 4th of July. This will probably come out after that anyway. But yeah. All right. See you guys. Bye.